Joined work with my previous supervisor, Anthony Lin. I'm in Barkhausen, but he's in University of Kaiserslautern. Yeah, so let's get started. First, I want to give a motivation example because, we want to. Now we use internet a lot. We have a lot of web pages. We interact with them every day. For example, here we have a small, the text input window. You can, like in Google, like in YouTube, you can write some comments there. So here you can write some text there. But there's some JavaScript code behind it. Its first one is the cat is a variable of the text you just input. And then for x, it just calls the function of HTML escape. It's a sanitizer. It will convert some characters to its HTML entity encode. After that, it just for security reason, we don't put what the users input into to transfer it to the server. And the second one is escape some strings. We also want to make some string not unsecure for the browser, also for the server. So finally, it will generate in the HTML. It will create a cat list. So if you just input some cat1, cat Tom, something like this, it will create a cat list. This is the intention of this code. But the thing is this code may have some bugs because we don't know whether HTML escape and escape string do their work correctly. So if we just input the flora and faun, okay, that's okay, because of step one, the HTML escape will just escape the characters of the end symbol. It's the HTML entity. And second, escape string will do nothing because no character to escape, so it keep it unchanged. Third one, just create a cat list. It works, everything works fine, no problem, no exceptions. But the thing is, some users may input others, like this one. It will input alert with some prefix and suffix. Finally, after the HTML escape and escape string, it will generate JavaScript functions. So when you click the button, it will jump out, something like this. This is obviously not what we want. And also for all the web developers, they don't want something like this. This means their code have something, bug. And here we just put alert there. Probably we could put other more, dangerous, risky functions here to steal some data from the users. So this means that filter the user input is very important for the security of web applications. But whether we to verify that the programs the users just wrote to make sure that we guarantee that the user input will finally be transferred to something, to transform to something legal and won't hurt others, won't hurt our systems. So we can use SMT servers here. We have 5 constraints. First one is we could encode the HTML escape as a function, right? And then put the result of the HTML escape to escape string function. After that, we use the concatenation. Here the plus is the string concatenation. We concatenate them together, we get the Z, and then we use the inner HTML function encoder to further transform it to the inner cat element in the ML. So this means we finally get the final string to be showed on the browser on your web page. But we need to check. The last line is say that whether it matches some unsafe strings. We can use regular expressions to express this string is unsafe. So when we put it there, we can check whether it matches or not. If it matches, that means our code have some bugs. This is what we want. But the thing is here, how can we model the semantics of these functions, HTML escape, escape string, or in HTML, these things, stuffs. We must have a mathematical models to model it and then verify it. So the solution is, our solution is the symbolic finite transducers. So it's, this slide I give some very boring but text definition of it, the transition label classic is just the transition label just characters from the alphabet. But in symbolic transducers, it uses like the predicates of a Boolean algebra. So it means that symbolic one. We always know that symbolic stuff more concise, succinct than other explicit one. And it also can support infinite alphabets, provide more efficient execution of the label transition operations. And the key advantage is to avoid the big alphabets, because for web applications, we may have like the Unicode. Unicode have like more than 1 million characters. When we try to handle them, we must be very efficient. Otherwise, it's useless for the web response. Yeah, but after this, we can think about like two simple examples to show like the power of the symbolic finite transducers. Like the left one is the classic one. We want to express that the transducer has some input. We want to accept input with only even numbers. The f is some output function. It means that we get the input 0, we will compute an output character based on 0. The thing is, this transducer want to accept all like even number sequences. Like 0, like 2, like 4, 6. The classic one, the thing is, the even number is infinite. So yeah, we can't use it to impossible to represent. But with symbolic one, we could just with only one transitions like here, x mod 2 equals 0. Then we can say that all the x satisfies this predicate, then we just accept it and compute the output function using f. So you can see that it's just one transitions. It can express infinite alphabet. So this is advantages for us, also for us to use to represent the application functions. I give another example, probably more easy to understand for the web applications. We have we want to match the pattern. The first is a sequence of lowercase alphabet A to Z, and another sequence of alphabet characters, big uppercase A to Z. But we want to use the transducer to transform all uppercase to lowercase, but lowercase to uppercase. So this transducer will do this work. So you can see that from Q0 to Q1, it just try to accept all the lowercase characters, and when it get it, we will output to upper function, change to its uppercase. Similar for the uppercase matching one. So like the example input is like when we input the big small, the output is not big small, but it changes the lower and upper cases. So this is another case or example of the transducers. Okay, now we give the formal definition of the transducer. It's for the status, it's quite classic, like NFA, DFA, something like that. It's like Q is the set of status, and I is the initial status, and F is the acceptance status. The only difference is about the transition relations. In symbolic setting, the transition is about two parts. First is predicates. We try to match a character uses predicates. And the second one is function f, the output function. And in Isabelle, we try to model it using some Isabelle symbols like here. We have Q and Q prime are two status for the transitions from Q to Q prime. And we also have the transition labels and two parts. First one is a set option, and another one is prime f is the function. Okay, so here we don't use any concepts from the Boolean algebra. We just use it's a set. We just said, okay, this label is a set, because all Boolean algebra predicate can be represented as finally it just denote a set. So we use this abstract definition to make it easier to prove and understand. The output function is just we give characters. We use option time because we want to support epsilon transitions, not only the characters in the alphabet. So it means that this update function could when the input is an epsilon transition empty string, it will also generate something. So this is the basic Isabelle definition. With the definition of the transducer, we define a key operation because I say we need to model the the web applications, HTML escape, all these are similar like a function or something. So, but how we do the computation is use the product operation. So it's the here we use the T to denote the symbolic finite transducer, and A is a symbolic finite automata. It's like the user input. The user input after the processing of the transducer is the result of the product. Some formalization details like the result may contain epsilon transition because our transducer contain epsilon transitions. And also we need to formalize the epsilon finite automata as well, not only the transducers. So I give two examples, like if the A is some strings or the Unicode, because the user can input all the Unicode string in the input window in your web pages, right? And the encoder, we have T is a transducer to encode the HTML sanitizer, and then the result is all the possible strings after the sanitizer, after sanitizing the input strings. Another example is okay, so the input is just a sequence of digits, and the T is just we replace this sequence of digits to a constant string number. Then the result of the product is number. So this is the intuition behind the product operation we formalized. The thing is, we want to use it to efficiently to do some verification for the HTML or web application sanitizing. The thing is, we need to have a good way to formalize it. And also we have, because Boolean algebra have a lot of different forms, like we have used intervals, we can use some arithmetics like x mod 2. All the different formalizations, we can't just, firstly we can't do them all of them at once. So we need a way to make it easy to extend to support different forms of the labels. So our way is to use the refinement proof. Refinement proof based on the work library of Isabelle. So in the most abstract level, we just model everything with the mathematical concepts like sets, like maps, or something like that. But in the implementation layer, we use another data structure to store the status. Here we use red blank trees or hash maps. We can do this automatically, almost free, because I think in Isabelle there's a very brilliant library. It's called the Refinement for Monadic Program. This is a very brilliant library. Then you can write logarithm in abstract level, but refine to efficient data structures like red blank trees and hash maps. So yeah, and finally the second layer. After second layer, but we still keep the transition labels as a Boolean algebra L locale in Isabelle. No concrete execution implementation, but in the last layer we will refinement to some, like in this paper we only refine it to intervals. So this is the basic idea of formalization. So to step by step, when you want to add a new Boolean algebra representation, you just need to update the last layer. The first layer is fixed, don't need to touch them at all. So it makes us easy to extend. And also with the hash map and red blank trees, it will be very efficient to execute. This is the Boolean algebra locale we define. It's in abstract level, we define the semantics of your Boolean algebra, what set it represent. And also a lot of operations like empty, intersection, difference, membership element, and together with a bunch of assumptions to define what is the correctness of your operation implementation. So our interval Boolean algebra implements this locale and then automatically integrate into the into the formalization of transducers. Yeah. So finally, we talk about the application and evaluation. The first one is, I say at the beginning of the motivation example, we want to do the sanitizer checking. We want to check, like, after the sanitizing, the output string when hurt our systems, when have some unsafe strings. So like for the single one, like the I is like, assume it's an input, and T is a sanitizer we model as transducers. So their product, the result is another language for the output strings. Then with the intersection of the A is some attacks, like unsafe strings sets. So, if their intersection is empty, means then, okay, so our transducer functionality is correct. It's satisfied what we want. And the second one is, like, in reality, not all the, sanitizer is not a single one. Usually a program will use a bunch of sanitizer to step by step. So we need like a composition of them. Yeah. So like the second one, we first use trim sanitizer and then use the HTML escape sanitizer. After these two steps, we get the result. We check with the tank strings. If they are empty, means then okay. So the composition of our sanitizers is also correct. Also work perfect. So this is the sanitizer checking. We give another example, like to show how to use transducer to model one of the sanitizers. This is one is from the anti-access attack encode HTML in C#. The input is a string T, like user input string T. So after like the first one is like if it's null, then it's written null. It's empty, then it's written empty. But the third one is if it is in the if branch means that it is safe. So we just pan it. We don't need to change the character. But for the other characters, we need to encode them into some code to the string final strings. So this is the sanitizer from the internet we pick, but this one is very easy to be represented, to denoted as a transducer like this. Just one status, two transitions. Like when it is safe chars, means safe characters, we just keep unchanged lambda identity function. But every unsafe chars, we call encode function to make it transform to others. Yeah. And we also to pick a bunch of sanitizers from the internet to evaluate the effectiveness and efficiency of our approach. For HTML, for JavaScript, for JSON, XML, CSS. So you can see that. So for the unsafe part, we deliberately to remove some of them. We find that when we remove them, they are unsafe. So this means that when we write or use the sanitizer, we must be careful to not miss some sanitizer, to not reorder some of the sanitizer to make it safe. But the verification itself is very efficient. All the verification is below the 0.02 second. So it's very efficient verification. Our another application is about string solvers, because in a few years ago we developed a string solver. String solver is a branch of SMT solver only for string series. So that one was also in Isabel, but it only supports very, very basic operations like equality, like concatenation, like regular constraints. The thing is, like they're not quite useful for the real-world applications, security analysis, because as I said, it needs string transformations, like from one string to another string. So because our transducer now, we have transducer now, so it could be used to model that. So we use it to model the SMT-lib supported operations for replacement, I just show an example. This is the example to replace the digits with the constant string number. So from the state Q0 prime to Q0 prime 1 prime is just to accept, okay, say all the digitals. And after that, it will replace it with number. So this is a basic idea. For the replace all, we model the replace all operations. So replace all has two parts: pattern. First one to match something unmatched don't match the pattern, and now they match the pattern. Then we use it with the replacement. Yeah, this is replace all idea. We also compare with some state-of-art assembly solver like Ostrich and CPC5. To our big surprise, actually, our solvers could beat the other two in most of the benchmark. Is expect the second line, the replace string CPC4-5 outperforms Earth and perform better than Earth. But it also shows that our service string solver could be used to really nullify some of the real world applications. So finally, I just want to express the expressiveness comparison with transducer. This is something talked about in SMT-Lib community, is that whether SMT-Lib should support transducer directly instead of with replacement. I give an example is replace each character in A to Z with its corresponding ASCII code. In transducer, it's just very simple, one state, two transitions. But if you use replacement, it will need 26 constraints. It's very long and ugly and give a lot of burden to the string solvers. It's not good. But in transducer, it will be very easy to solve. So, but now I haven't yet support. But if it support the solver could easily to support the transducer as well. So finally, is some side dishes. Not only the transducer, we have now have a complete, pretty big library for the FA and the NFA and the transducers in symbolic setting. If you are interested, you can try some of them. And finally, the contribution is we formalize the first SFT, and we use the refinement approach to improve its efficiency, flexibility, and tension. And yeah, we also applied to two applications. Yeah. Yeah, that's it. Thank you.
We can take a quick question, but if the next speaker can also set up the. Thanks for that talk.
Thank you.
Do you have any intuition what the other SMT solvers are doing wrong and what you are doing right? Is it just the fact that you're using the transducer representation? And
yeah. I mean, that's a good question. Because when I got the experimental result, I was surprised, very surprising to me. Because a deep comparison with them is hard to say, but I can just say some potential reasons. Firstly, the other two solvers, they try to cover all the features of the strings and try to cover the complete set. But ours, when we encounter something, we find that we can't solve it, we will just give it up. Another reason is like for Ostrich developed in Java, Scala or Java, it was JVM, so mostly they will run slower than other languages. For CPC5, it was a different way, not different logarithm. They use word equation theory to do the solving. I'm not quite sure because I didn't find some benchmarks uploaded by the CPC5 in SMT-Lib. So if they have, probably we can compare them. But now we can only find these benchmarks they can't solve. But probably the word equation theory problem, yeah, that could be.
All right, let's thank the speaker again.